So I don't think Ingrid needs any introduction. So Ingrid Daubechies.
So, hi.
5 minutes.
I apologize for coming in. I mean, I was on standby delays yesterday, standby this morning. Okay, so I'm going to go, these are the slides I used for a talk I gave at the ICIM conference last week. And then Larry asked me to stand in for Rafi because Rafi couldn't make it, and he thought this kind of introduction to sparsity might make a good idea, might be a good idea. So without further ado, if I learn, okay. So, well, sparsity has had an emergent role over the last 4 decades. We've learned it as a powerful tool for data analysis and computation, which was the theme of my talk, and better understanding. But here, I mean, you're all convinced will have a tremendous impact, and we're all working on that. So, let me take image analysis as an example of how we came to sparsity. So an image is just a function on a rectangle to 0, 1, or to if you quantize it. You can sample it, you can average it. In any case, you can also view it as a function on a discrete grid already. In any case, it's something in a very high dimensional space. And for practical purposes, we need to compress it, we need to store it, transmit it, analyze it. So how do we do this? Well, it used to be, I mean, and we still believe that if you have a whole class of things, you should use its mathematical properties to do that. And it used to be that what seemed to be very important in images was the fact that as a class, they are translation invariant. I mean, if you think of a scene, then it's obvious that you can take different pieces of it and they're all going to be perfectly valid images. So the class has translation invariance. And that means that it's very natural to look at the Fourier analysis, which gives you the irreducible representations for the translation group, is going to be important in analyzing images. And indeed, if you look at a JPEG standard, that uses DCT, which is this discrete cosine transform. And the building blocks of the DCT look like this. The JPEG standard uses DCT on 8 by 8 blocks. But if in the early 80s, late 70s, early 80s, people were believing that that was really for technical reasons. That as we would get faster and faster chips, we would get to 16 by 16 and eventually even 256 by 256, which was what people were thinking then of as the size of an image. And that didn't happen. And in fact, I remember seeing talks where people went to 16 by 16 and they weren't doing better. And in fact, in the 80s, what happened instead is people started using wavelet transforms for images, and which is a completely different type of building block. And well, you've all seen pictures of wavelet. So we have the high frequencies and the lower frequencies, but we have them at different scales. So there's and a wavelet basis typically is not translation invariant. So high frequency wavelets are much more narrow than the low frequency wavelets, and so you need many more to cover the whole image width and height. And that actually is something that you recognize immediately in traditional representation of wavelet decompositions of an image. I mean, well, this is fairly standard. You have you have 3 rectangles that give you the fine scale wavelet coefficients. You need that larger rectangle because you have many fine scale ones, and then you have them 3 that are smaller and that give you the slightly coarser scale, and then coarser scale. If I had a pointer, I could point, but I mean, you probably know how it works anyway. So that shows that indeed I need many fine scale ones, and then some coarser scale ones, and then even coarser scale ones, and so on, to cover the whole image. And we can see how the different layers build up the image by actually going ahead. Oh, thank you. So. So, the rectangles I was talking about. Okay, so, and you can use that for compression. I mean, here, if I take out of all these fine scale coefficients only certain of them, this is the image I reconstruct, and of course it's not perfect. I mean, I can toggle back and forth. And if I take even more, then I virtually get the whole image. So that's what wavelets do. And the JPEG 2000 standard uses wavelets instead of DCT. The major reasons why it uses wavelets is that it allows for graceful degradation as the rate drops. It makes it easy to implement something where you can choose between lossy and lossless. The impact it has had, well, none on consumer products. I mean, that I can see at least. The reason for that is that you remember how expensive memory was around 2000 and how cheap it has become? We don't care anymore how much we compress. You can, but it has made an impact. I mean, digital movies within the US and in Europe, in movie theaters, will use JPEG 2000. Sports reporting also on digital television uses JPEG 2000. And actually, I first noticed that by noticing that as my husband was watching a soccer game, that the artifacts in the grass, which of course nobody pays any attention to except people who are not that interested in soccer and who are interested in image analysis, the artifacts in the grass, you can very clearly see that those are wavelet artifacts. Okay, so, but why have we, I mean, we're all used now to using wavelets for images. What was wrong instead of the DCT? What was wrong? I mean, there was nothing wrong with it. The difference is really one between what Ron DeVore calls linear and nonlinear approximation. So let me tell you about that. If you have a class of functions, let's take just nice class of functions on the torus, so on the circle. Let's consider a class of such functions, nice functions. And let's imagine that we take a measure, a probability measure on this class of function that's invariant under translations. Meaning that if I take a set of functions and I translate that whole set of functions, then it will still have the same probability. Then it's easy, and you use Cahoon and Loewe arguments to show that the best basis in which this class can be reconstructed is the Fourier basis. That's to say, if you want to find the basis of functions so that when you project on the first one that the expectation of the error is the least possible, or you expect on the first n of them, you build your class, your basis one by basis element, and for every truncation you want the error, the expected error, to be minimal. Then you can prove, because of the translation variance, that you have to use a Fourier basis. So let's now look at an example of a class of functions, which I build as follows. I use a Poisson process to throw down some points. And then that number of points, remember my interval 0, 1 is really curled as a circle, is now cut into, in this case, 4 intervals, the 0 and 1 tied together. Let's take then I have another process that generates nice and smooth functions. So let's take, because I have 4 intervals, let's take 4 realizations of that process. And let's now, on each of the intervals, just take one restriction of this function. And I retain those pieces of the function. So I have made a very simple process. It's translation variant, because my Poisson process was translation variant, and the other process was also. I have a translation variant process that generates functions that are constructed out of pieces of smooth functions. It's Clantratian invariant. With this process, you can prove, because it's so simple, you can prove that with the ENs here are the Fourier basis, you're bounded below in error by 1 over n. But you can find very easily with wavelets a strategy that gives you a better bound than that. I mean, all you need to do is you need to, if I'm allowed to use capital N coefficients, I'll use half of them on all the wavelet coefficients, I fill all my layers, and then from then on, I only put them below discontinuities. And you can prove, I mean, depending on how smooth the functions were, but you easily can prove for nice and smooth functions a bound like n minus 2. So you're doing much better with wavelets than you were doing with the Fourier basis, because they're at a lower bound in 1 over n. And the enormous difference is that in one case, I was trying to make the truncated sums, if I took the first L terms every time, to be as small as possible. In the second case, I allow my L terms, the ones that I retain, to be the ones that are the most powerful for that particular function. So in the first case, I was using my basis to build bigger and bigger subspaces, and I was trying to govern things by means of the distance of f to the subspace, and that's linear approximation because I have these linear spaces. In the second case, I was looking at basis elements, and I was looking at all the collections I could make by using only n of them, and that's a very spider-like non-linear set, and I was looking at that. So that's the difference. So wavelets were powerful, we said before, earlier we would have said, because they're good at nonlinear approximation for images. But in fact, it's really what we were saying was that images have sparse wavelet expansions. We can expand them well in these bases with few terms and have a very good approximation. So that was, with hindsight, wavelet expansions were the first example of benefit of sparse expansions. Now, why wavelets have this property, that is linked with a whole lot of beautiful and strong theorems in harmonic analysis. And in fact, if it comes down to it, for 2D images, wavelets are not really the best basis. You can do better with curvelets or shearlets. But in any case, what we have is a situation where with images, we had guessed a good basis. Because of mathematical arguments, because of what we believe about images. The question now is, and a more modern question is, can we search for a good basis for sparse expansions? If we have a whole class, can we find these bases? And we can do that within dictionaries, so unions of many, many bases, or we can do that with nonlinear adaptive decomposition methods. And I think we will hear much more about that in this workshop. Okay, if we were searching a whole dictionary, what that means is that here, you're given your f, and you have a whole lot, you put all this union of bases next to each other, and you're trying to find rare coefficients, so a number of in an enormous column vector, just a few entries, and this selects which of the columns you're going to use in order to make your f together. So what we're doing here is putting it, writing f as a possible linear combination of a whole lot of different elements in a dictionary. And that is something that looks very much like compressed sensing. In compressed sensing, you try to write, your idea is, if you have something like images, then they can be put together as a sparse expression of wavelets. But why first acquire the whole image to decompose it into wavelets and to find that? Maybe we can acquire the whole thing sparsely. And that's what compressed image tries to do. It tries to make, given a vector, we can determine that vector by making much fewer measurements. I mean, so the idea is, now I have a vector. Here on the right, I have my XLs, which are the different coefficients. I want to try to make a whole measurement, so measurements that are much fewer than the total dimension of the space. So the blue matrix now is not as high as the whole dimension of the green vector, and that shouldn't have been x, that should have been y, I apologize. And what we try to say is, instead of trying to acquire x and then compress it to, why can't we acquire a much coarser column vector in order to get the whole thing? It's the same picture as we had earlier, it's just a different emphasis. And what compressed sensing tells us is that the answer is yes here. So compressed sensing is related to results in theoretical computer science, just like there were powerful results in harmonic analysis that really led to, that were underlying all of wavelets. You have these very powerful results in theoretical computer science, Johnson-Lindenstrauss lemma, and a whole lot of constructs that were built from it that tell you that you can find a geometry, that you can render the geometry of vectors in a high dimensional space by random projections on much lower dimensional space without really serious loss, if you do it randomly. There's an element of probability in there. And that underlies the idea of why we can build such compressed sensing. So those results in compressed sensing had a tremendous impact. I mean, you could, the early results in the 80s on building probability proofs that you could check with high probability by some random sampling in the proof were based on it. They've led to fast computation algorithms, by Anna Gilbert and Martin Strauss and many other people. So here actually I give an example of such. If you know that a function exists in a high dimension and has a very sparse Fourier transform, which I forgot to write here apparently, then you can actually find that and compute the right by only taking the order k log n samples, where k is the number of non-zero entries and n is the dimension. Okay, so what this tells us is that knowing or believing that there is sparse expansion can be exploited to reconstruct from seemingly very insufficient data. It's a very powerful idea. We can do that with compressed sensing in a dictionary, searching in a dictionary. You can also try to learn the dictionary of a given class of objects. And here I'm taking images that were built for a poster of a program at the Institute for Advanced Study on a few months ago, but that were really made using software from Larry Caron's group, where they used it on some French chateau or something. The idea is here on the left you have the original image. In the middle you have an image of which I have given you only 20% of the red, green and blue pixel values. So for many pixels I have nothing. For some of them I only have one of the colors, and that's why it has this funny look. And then from this, knowing that there is a sparse basis, but not knowing from the start what that basis will be, you can reconstruct a right. So just from this one image, so the notion of imageness in a certain sense is already embedded in that one very, very corrupted image. Okay, so yeah, and let me just not go through these. These were, I mean, here is my final slide. I mean, I have talked about results of many different people and given only a very few names. And so this was my slide about apologies to all the people who I haven't quoted by giving full references during the talk. But so the whole message of it, and this was a message that I had 2,000 people listening to at ICIM, is we have seen things like wavelet expansions show that sparsity was important. That's really the message. I mean, it was just one example of how important sparse representations are. If you know that something is sparse, you can really exploit it to do very powerful things in computation and in data analysis. And that's what we will be doing this workshop. Thank you. Yes. 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 But it's not an approximation with I mean, where you're exploiting that, and I think what we're basically exploiting, what we may be exploiting ultimately is also something about how our visual system works, quite honestly. You're exploiting imageness, and that's how our visual system works, in order to take small blocks and from that learn what for this image are the right things to learn. And I believe, I mean, there are very nice papers by Portugal and his group that actually try to build up a way of measuring distances between image in a multi-resolution way based on what they have measured about retinas in experiments, and where you take small building blocks and then use how things score with respect to time plates in small building blocks in order to build distances at a higher level. And I think what you do is you build a way